Hey everybody, let's check out this problem here. We're going to find the limit as x approaches infinity of this crazy looking function sine squared x divided by x squared plus 1. Let's just take a little trip down here to look at y equals sine x. That one is one of those functions that we all memorize in our trig class. Okay, so that's 2 pi, and here's x, and here's y. The maximum's 1, the minimum's -1. Maybe I should use graph paper, make it look a little nicer. But I want to point out that the limit, so this is y equals sine x. I want to point out that the limit of sine x as x approaches infinity does not exist. Because, well, I mean, we could prove this more precisely, but one thing I will tell you is if the limit did exist and it's a number, that would imply, it would follow that there is a horizontal asymptote. So if you have a limit as x goes to infinity and you get a number, the limit equals 0, for example, then you would have a horizontal asymptote of y equals 0. There's no horizontal asymptote. Sine x, as we see, and as we should know, oscillates between -1 and 1. Now, let's just, assume that we know that sine graph. That was one that people memorize, etc. Let's look at now the graph of y equals sine squared x, which is not one that people usually memorize, but remember that if you square a number, the result cannot be negative. The graph looks something like this, but I'm not saying that would be like something where you would, want to base your homework solution on. This is just a rough sketch. Better look up a Wolfram Alpha to get the really good one. But that's, roughly, this is what the graph looks like. Okay, and again, the limit does not exist. We can see that this does not exist because what I can see is there's no horizontal asymptote. The graph oscillates. Now, between 0 and 1. So this is pretty long-winded. I want to talk about this guy. Do we know this limit even exists? The answer is it does, but we shouldn't assume that it does. We have to prove that. That's really part of our proof, is not just finding the limit, but showing the limit exists. So one of the things that I get out of this graph here, and by the way, we don't need to sketch this graph to understand or to do this proof. But one of the things this shows us right off is that sine squared x is between 0 and 1. But I don't suggest, that we sketch this graph. It's not a graph that we usually memorize. But if you think about it, we do know that sine x is bounded between -1, as a minimum -1, and +1. And when I square sine x, the minimum now is 0 because the result of squaring a real number is never negative. And actually sine of 0, sine of pi 2 is 0. So our minimum is 0, our maximum is 1. And what I'm going to do is I'm going to use the squeeze theorem to prove that this limit here is 0. So let's write that on the top. We use the squeeze theorem, aka the sandwich theorem. Okay, so squeeze theorem, which is also known as the sandwich theorem. Sometimes different textbooks like to mix up the names of things so that they don't look like complete copies of each other. But some books say squeeze theorem, some say sandwich theorem. Why sandwich theorem? Because we have like a little sandwich. This sine squared x is sandwiched between 0 and 1. But what we want to do is have sine squared x divided by x squared plus 1 in our sandwich. Now, what I'm going to do is I'm going to have that as the middle of our sandwich, because that's the one we're trying to find the limit. What I do is I divide by x squared plus 1. Keep in mind that if you multiply or divide by a positive expression, it does not change the direction of your inequality. If I say take this guy and multiply by -1, if I multiply by -1, all the inequalities would change directions. We don't have that issue here because x squared is never negative. Therefore, x squared plus 1 is never negative. This whole thing's never negative. So we can do that. Now, sine squared x is now sandwiched between two functions which I feel I can really get a handle on. I can find these limits. What is not allowed, we're not supposed to do this. We're not supposed to say, okay, I'll put limit here. What's wrong with that? Why can't I do that? Because we don't know that this limit even exists. So that's not allowed. You might get the answer right on a multiple choice test, but mathematically that's not correct because unless someone told us that this limit exists, we don't know this limit exists. So I'm not going to do that. And that's not the squeeze theorem. That's a comparison theorem. Okay, so the squeeze theorem is easy to use though, if I can set up the inequality. The inequality is the hard part. We already did that. Limit is 0, 0. The limit of 1 over x squared as x goes to infinity is 0. Well, this is 1 over x squared plus 1, but let's talk about 1 over x squared. There's actually a theorem that says that's equal to 0, but you can just think it through. Put x is 1,000,000. Put the denominator x is 1,000,000. You square it. That's 1,000,000 squared, even bigger. 1 over this huge number. It's not equal to 0, but the limit is. It gets very close to 0. Now, if I put plus 1, we're also going to get 0. You could do a more complete proof of that, but let's not get carried away. Large number squared, even bigger. Plus 1, bigger just by 1. If that's in the denominator is huge as x gets large. 1 over a very big number becomes very small, close to 0. As close to 0 as we want. Therefore, the limit of this inside function exists and it's equal to 0. I wanted to just point out that my notation here might not be super neat. Let me make a smaller marker. I might want to write this little 2 up here around this. That's not sine 2x. That the whole time through, in every single instant here is sine x. It's not sine 2x, it's sine x raised to the second power. Sine x times sine x. It's like that, okay. And why is that true? By the squeeze theorem. The numerator, the limit, why do I have to use the limit, the squeeze theorem? Because the limit of sine squared x does not exist. The limit of 1 over x squared plus 1 is equal to 0, but you do not multiply a non-exist by 0 like a limit law. So you have to use the squeeze theorem. Well, I think you do. You could also use you could use the definition of start pulling out the epsilons and definition of limit to do this problem. That would be more sophisticated, but that would go pretty well too. That's pretty quickly if you do that also. But we're not, that would be more like an upper division math problem, and we're not going to do that. Those techniques of using epsilons, leave that to a more upper division math class, which are super fun. I don't think you'd regret taking upper division calculus because it's so cool. Alrighty, so I'm not making any money off this. This is all for education, so I hope it helped, but there's room for improvement. Things could be better, but anyway, that answers the question, and I think I'm pretty sure all the math there was correct. So, but maybe I could have explained better, but alrighty then, everybody stay safe out there. Okay, take care, bye.